Today, we're digging deep, way deep, into the story of the energy that has powered our entire modern world for more than a century: fossil fuels.
It sounds like a pretty wild question, right? But the answer connects millions of years of our planet's history directly to the gas in your car and the light switch on your wall. So let's start at the very, very beginning.
Okay, I want you to picture this. Our story kicks off hundreds of millions of years ago, way before humans were even a thought, on an Earth covered in lush, steamy swamps and vast oceans. So you've got two main pathways this all happened. First, on land. Think of these enormous ancient swamps, just filled with massive plants. Well, they die, get buried under layers of muck, and over time, you get coal. Then you've got what's happening out in the seas. Tiny little marine organisms and plants die, sink down to the bottom, get covered in sand and silt, and that's the start of the journey for oil and natural gas.
Think of it like a geological recipe. You need three crucial ingredients. You start with the organic matter, of course. Then you add immense pressure. We're talking layers and layers of rock piling on top. Then you add intense heat, cooking it from deep inside the earth. And the final, most important ingredient? Time. Lots and lots of it. Millions of years for this whole thing to bake. If you miss any one of those steps, it just doesn't work.
So, on a chemical level, what is this stuff? Well, it all comes down to one thing: hydrocarbons. These are simple molecules made of hydrogen and carbon. The best way to think of them is like tiny little batteries, each one charged up with sunlight from eons ago. So the real power isn't in the black goo itself, it's the energy locked up tight in the chemical bonds between those atoms.
But getting this energy-packed stuff out of the ground is really only half the battle, because in its raw form, it's not very useful. First, we've got to unscramble it. Yeah, that raw stuff we call crude oil is basically just thick black gunk. It's a messy jumble of hundreds of different kinds of hydrocarbon molecules all sloshing around together. You definitely can't just pump that straight into your car. It has to be sorted out first. So how do you sort a liquid? It's actually pretty clever. It all happens inside one of these, a massive fractionating tower. The process starts by heating the crude oil until it becomes a vapor. This hot gas then rises up the column, and as it gets higher, it starts to cool down. And here's the magic trick. Different hydrocarbons condense back into liquids at different temperatures, so they collect on these trays at different levels, neatly separating them. And this is what you get. The really light molecules with low boiling points, they zip all the way to the top and become things like LPG gas. A bit further down, you get the stuff we all know, gasoline for our cars. Lower still, you've got kerosene for jet fuel and then diesel for trucks. And way down at the bottom, you're left with the thick, heavy stuff that barely vaporized at all. That becomes bitumen. The stuff they use to pave roads.
So you see the pattern here, right? The size of the hydrocarbon molecule basically determines everything about it. The smaller, lighter molecules evaporate easily, they're runny, and they're super flammable. But the bigger, heavier molecules, they're thick, sticky, way harder to set on fire, and they tend to burn with a lot more soot.
All right, so we've dug it up, we've sorted it out. Now for the most important part. How do we actually get the energy out? Well, it all comes down to a very simple but incredibly powerful chemical reaction. The key concept has a fancy name. It's called an exothermic reaction, but all that means is it's a chemical process that gives off energy, usually as heat. The stuff you start with has a ton of energy locked away, and the stuff you end up with has less. All that leftover energy gets released into the world.
And the most classic example of an exothermic reaction is, of course, burning. We call it combustion. When we burn hydrocarbons, we're rapidly breaking those chemical bonds and releasing all that stored up ancient sunlight as a massive amount of heat. And that heat is what does all the work, boiling water to spin turbines or pushing the pistons that make a car go.
But here's the thing, how you burn it really matters. If you have plenty of oxygen, you get what's called complete combustion. It's efficient, and the only things you produce are harmless carbon dioxide and water. But if you starve the fire of oxygen, you get incomplete combustion. This wastes energy, and even worse, it creates all sorts of nasty byproducts like poisonous carbon monoxide and soot.
And those nasty byproducts, well, that's where this whole story takes a pretty serious turn. Our massive reliance on this ancient energy has some very real and very modern consequences for our planet.
When we burn fossil fuels, it releases a whole cocktail of pollutants into the air. Sulfur that was trapped in the fuel creates sulfur dioxide. The extreme heat inside an engine actually forges nitrogen oxides from the air itself. And as we saw, incomplete combustion gives us poisonous carbon monoxide and soot. Every single one of these is harmful. And here's how just 2 of those cause a huge problem: acid rain. It's a simple process. First, sulfur dioxide and nitrogen oxides float up into the atmosphere. Second, up in the clouds, they mix with water vapor and form acids. And third, that acidic water falls back to Earth as rain, which can damage forests, harm life in lakes, and even eat away at stone buildings.
Now let's talk about the main byproduct of even a perfect burn: carbon dioxide. Normally, CO2 is a natural, essential part of something called the greenhouse effect. Our atmosphere acts like a blanket, trapping some of the sun's heat to keep our planet warm and cozy. Honestly, it's a good thing. Without it, Earth would be a frozen rock.
So what's the problem? The problem is we've been pumping huge amounts of extra CO2 into the air by burning all these fossil fuels. It's like we've thrown a second, much thicker blanket on top of the planet. It's now trapping more heat than it should, and the result is a clear, steady rise in the Earth's average temperature. And that's what we call global warming.
So these impacts are obviously pretty serious, but engineers have developed some really clever solutions to try and reduce some of the harm.
Take this for example. It's a catalytic converter. You have one in your car's exhaust pipe. Inside is a honeycomb structure coated in precious metals like platinum. As the toxic exhaust fumes pass through, these metals trigger chemical reactions that convert poisonous carbon monoxide and nitrogen oxides into much safer things like carbon dioxide, nitrogen, and water.
And this fight is happening on multiple fronts. We can refine fuels to get the sulfur out before we even burn them. Power plants can install scrubbers in their smokestacks to capture pollutants. And we can also make a switch to fuels like LPG that just naturally burn a whole lot cleaner than heavier oils.
But beyond all the pollution, there's a more fundamental issue here. These fuels, which took millions and millions of years to form, are finite. We are using them up at an incredible rate. And once they're gone, well, they're gone for good.
Which really leaves us with the ultimate question. We built our modern world on this buried power, but it's a legacy that comes with both a time limit and a very steep cost. So the great challenge of our time is to figure out what comes next. What's going to fuel our future?